So let's talk about the first one. All of these perspectives get around to the concept that our frequency domain explanation of what the system transfer function is doing is a complete explanation of how it can transform any input signal to any output signal. And the first perspective is that it's completely equivalent to the time domain difference equation. Just abbreviate that, difference equation. And you know that the difference equation is a complete description of what our system does. So therefore, the transfer function is going to be a complete description of our system. So let me give an example of what I mean by this. Let's say we've got a simple difference equation that looks like this. Now, you already know that this is a difference equation, and it's a complete description of what our system does. And given this in the time domain, with an input, you could figure out the output. You've done this before. In the frequency domain, since that's this chapter, our y of n becomes a y of z. And Stone, what does this next component become? We want to transform this difference equation into the frequency domain. So what's the transform of 1/2 y of n minus 1?
I'm not sure, sir.
What's the transform of y of n? You can see it over here.
Y of z and z.
So in general, a y of n is y to the z. And then how do you account for the fact that it's delayed by 1?
You just multiply it by z to the -1.
That's it. We can do the same trick over here. And this would be times z to the -1. So now we can group our y of z's and our x of z's together. And what we're trying to do, big picture here, is come up with the system transfer function. And by grouping them using the distributive property, we only have one mention of our x of z and one mention of our y of z. And now we can create our transfer function. So Cole, we know we define our transfer function in the frequency domain to be the y of z over the x of z. And for this particular example, what's in the numerator?
The numerator would be 6 plus z to the -1.
You got it. And then the denominator is the other one. The mistake you did not make would have been a really common one for cadets to put the wrong thing in the numerator. The point of all this is that this is a complete representation of our system. Second is you can see where it comes from directly from the difference equation. We're not doing any kind of complicated table lookups or any complicated transforms. You could directly read out this h of z, once you've got a little practice, from the difference equation. The numerator is the right side dealing with the x's, and the denominator is the left side dealing with the y's. So it's a direct one-to-one transform given the difference equation. Since you know that the difference equation fully specifies your system, therefore the transfer function in the frequency domain's got to fully specify your system too. And although I've drawn it as an h of z, since we know that the z can be replaced by e to the j omega, we could have just as easily represented this as its dtft. So from now on, just because it's a few less strokes to write in terms of h of z, I'm going to write it in terms of h of z and realize that it's trivially converted over to its dtft counterpart. The things I want you to walk away from this is that h of z, or equivalently h of e to the j omega, which are frequency domain characteristics, descriptions, directly and trivially transform to and from the difference equation, which is the time domain description of our system. So no tables. And the second thing is that if you're given an x of z and the difference equation, then you can find the output by Ben. So you're given the x of z and you're given the difference equation, which this just showed how easy it is to convert it over into a system transfer function. And now how do you find the output?
Aren't you just plugging it in for each value?
Well, you've got your h of z, absolutely. And then what do you do with your h of z to find the output? You got to multiply it by
your x of z.
your x of z. So the point that I'm making here is that if you're given that difference equation is everything you need to know about your system, and then it's trivially easy to get your output given the difference equation in the frequency domain by doing a one-to-one conversion of the difference equation to the transfer function. So big picture, what is the transfer function? One way is it's just a rewriting of the difference equation in the frequency domain. That's what I want to get across here.